Okay, hold on. Never mind. To get to your test scores, it's in the it's under Unit 1 test score, and it's got like a sheet that you have for you. Yeah, and you can get to it from there. You can just take a look. It's got the raw score, and then it's got the you don't have to turn it in. I'm giving that to you so that you can see. And in order for me to be able to give it to everybody individually without giving everybody scores to everybody, I had to make it an assignment, but it's not an assignment. It's just a way for me to be able to give you your test scores now, because I know a lot of you were really curious about that, especially when being told that you got a 0. So you don't have to turn it in. I've got the scores already. I just have to put them in, and I haven't had the time to do that, but I'm going to try to make the time. We're good. All right. So we need to talk about the basic fundamental building block of the entire body's nervous system, the neuron. Now, when we talk about the biological bases of behavior, we're talking about things that, if damaged, could affect how you react to things, how you behave, how you do things. So the nervous system is made up of billions of little tiny nerve cells called neurons. Your brain is made up of billions, if not trillions, of these little tiny cells that are interconnected together and communicate and form everything that we know. Everything you've ever seen, everything you've ever heard, everything you've ever remembered, all in neurons in our brain. Okay? So we'll talk about neurons in the nervous system this week. Next week, we're going to talk about the structure of the brain itself. And then the last week, we'll talk about another communication system in our body, the endocrine system. But for right now, we need to talk about the nervous system and its basic fundamental building block, the neuron. The neuron can look very different depending on what kind of a neuron it is, but most neurons all share a similar structure. Off of one side, they have dendrites, and those dendrites reach out like branches of a tree to other neurons, okay? The dendrites feed information to the cell body, which then can shoot electricity down a single strand going away from the cell body called the axon. The axon ends at these little tiny bulbs at the end of the axon called either end bulbs or axon terminal or axon bulb. And inside those bulbs are little chemicals called neurotransmitters, and we'll talk about those in just a second. So neurons communicate through a chemical reaction. Chemicals are sent from one neuron to the next, and they are absorbed by the dendrites. The dendrites, which are reaching out to different neurons that are surrounding that neuron, send that information to the cell body, which either can fire or not fire. If the neuron fires, it sends a tiny amount of electricity down the axon to the end bulbs, which releases neurotransmitters that go to the next neuron and the next and the next and the next. Okay, so that's how your neurons are basically function. And this is kind of the basic setup of what a neuron looks like. It's dendrites, a cell body, an axon, and end bulbs. They can look a little bit different depending on the job of that neuron, whether it be something that is between one set of sensors and your brain, or something that attaches to a muscle fiber, which allows it to move and be controlled by your brain. There's lots of different things, but they all basically have dendrites, a cell body, an axon, and an end bulb. Okay, that's the basic biology of the cells of a neuron. Now, neurons can go wrong in lots of different ways. For example, you'll notice that there is a sheath of myelin or malin. This little fatty material that covers the axon basically acts as an insulator to the axon, because the axon is acting like a wire, okay? Because it's shooting electricity. And if two axons were to touch each other, you'd have a misfire where one neuron is sending information, and then it short circuits to another, and the message doesn't get to where it's supposed to go. And that can cause some severe problems and issues, which we'll talk a little bit about. But there's lots of different neurological disorders that can arise. All right. So at the end bulb, neurotransmitters are contained, and there are a number of different neurotransmitters. These are some of the big ones, and we'll be talking about these throughout the year in kind of passing reference. So I want to make sure that you get that there's a lot of different kinds of chemicals that are inside our brains that allows us to function. For example, we have acetylcholine. Acetylcholine causes the contraction of skeletal muscles. It also helps to regulate your heart rate and promotes arousal in the brain. And when we talk about arousal in this class, we're not talking about sexual arousal. We're talking about like being aware. Okay, so it allows your muscles to move, your skeleton, so you can move. It allows your heart rate to be regulated. It promotes paying attention and transmits messages between the brain and the spinal cord. Now, people who have low levels of acetylcholine tend to have low levels of arousal and low attention. And that depletion of acetylcholine has actually been associated with Alzheimer's disease, which is kind of a frightening disorder that can arise when things go very, very wrong. Okay, so that's acetylcholine. Glutamate stimulates receptors associated with learning and memory, as well as many sensory and motor functions. Glutamate is an excitatory neurotransmitter, which means it causes the neuron to fire. Okay, so it excites the neuron so that it'll shoot electricity down the axon. An overabundance of glutamate may lead to migraine headaches. Back in the 1970s and 80s, there was a large-scale fear of something called monosodium glutamate, or MSG, and it was an ingredient in processed foods to make it taste good. And there were people who began getting these really bad migraines, and they started to think that it might be the MSG that they were eating, because they were eating a lot of MSG. And so being anti-MSG became very, very popular in the very early 1980s, kind of like the gluten intolerance from a couple of years ago. Everybody, this got gluten in it. Ooh, gluten. Yeah, you're fine. Most people don't have a gluten intolerance. Okay, just like most people aren't that sensitive to MSG, but it was put on everything. No MSG. It actually got a name called Chinese restaurant syndrome, which was where you'd go to a Chinese restaurant and you'd eat, and then you'd get home and you'd have this really bad headache. And the people who came up with that study believed it was the MSG that they were putting into the Chinese food. But that was just actually racist, because they were trying to find a blame and they put it on Chinese food. MSG actually naturally occurs in lots of different things that you've probably eaten. It's probably been in, you're probably eating something right now that has MSG in it. They don't call it MSG anymore because it's kind of a name that nobody wants to be associated with, but it just makes food taste better. That's all it really does, is it adds a flavor to the food that if missing, you'll go, this doesn't taste good. It tastes like the box. I don't want to eat this anymore, and you won't buy anymore. But if they put a little MSG in there, ooh, this tastes good. I like this. Um, GABA, or gamma aminobutyric acid, inhibits the firing of neurons. So it is the most abundant inhibitory neurotransmitter, which means it stops the neuron from firing. GABA is associated with calming effects in the brain. A lack of GABA is connected to seizures, tremors, insomnia, anxiety, epilepsy, and Huntington's disease. So there's lots and lots of things. If you lack the neurotransmitter GABA, can actually make it so that you have a bit of a tremor, or you might end up getting seizures, or you suffer from insomnia, anxiety, all these different things, because your brain can't slow down. Okay, think of GABA as kind of the brakes on the car, whereas glutamate is a little bit of the gas pedal. It excites the brain, and GABA calms the brain down. Okay. Dopamine is probably a neurotransmitter that you've heard of. It involves the processing of smooth and coordinated motor movements and attention in learning. So the fact that we can, very calmly, wave our arm back and forth, that is because of the neurotransmitter dopamine. Now, a lack of dopamine, or a lower abundance of dopamine, means that your movements are going to be a little bit jerky and not as well coordinated. Dopamine has been, or a lack of dopamine has been associated with Parkinson's disease, which is you have a tremor in your hand or in a body part, and you simply can't control it. No matter how hard you try, it doesn't stop, and that's because the dopamine neurotransmitter in your muscles just isn't functioning and isn't doing well. This can also dopamine is also used in especially things that develop addiction. Dopamine is released, and it makes you kind of feel a little bit better. For example, there are people who have suggested that phones, the modern smartphone, is actually a dopamine machine for us, because whenever you get a text message or a phone call, or you're on Facebook and you get a like, or you're on Instagram and you get a thumbs up or something, it just gives us a little bit of a hit of dopamine in our system, and that makes us feel better and we want it again. A lot of times people develop
that just happened to me. As soon as you said that, I got like 3.
Yeah. It's really highly addictive. A lot of times people are addicted to substances, but they're more addicted to the hit of dopamine that they get by using that substance. For example, nicotine is highly addictive, but the longest a nicotine craving will last for is 3 minutes. If you can make it past 3 minutes, you're no longer craving nicotine and you can go on with your life. So why is it so difficult to stop smoking? It's the dopamine hit that you get through the process of smoking that cigarette, that relaxation, that good feeling that you get by doing it. It's not the nicotine, it's the dopamine that your brain is feeding to you. Okay. So, the entire process is really, really addictive and can cause some very serious problems for people who are addicted to drugs, or addicted to sexual activity, or attention-grabbing experiences like playing a game. They're basically game design is a lot of psychology, especially a lot of the stupid games that people play on their phones. Why on earth do people play a miniature pool for hours on end? That's all I saw last year and the year before. People playing pool on their phones. And I'm like, you would never play pool in real life. Why are you playing it on your phone? Because when you get that ball in the hole, it gives you that little hit, and it keeps you coming back for more. Okay, so it's not that the game is addictive. It's that the behavior that we have gained from it, the hit of dopamine, that's what we keep coming back for. It makes us feel good. You want to look at it again. Oh, somebody text messaged me. What did they say? Oh, I feel better. Okay, good. And now I just wait for another one and it'll make me feel good again. Okay. Now, I'm not saying it's like heroin and you're just like whacked out, like, but you get the idea. It just gives you a little taste of, this is good. I like this. This is good. Keep doing this. Okay. Norepinephrine is another neurotransmitter, and this is found in the autonomic nervous system, which we'll talk about in just a second. It governs sympathetic arousal by activating heart and blood vessels, thus giving rise to our fight or flight response. So if we were to experience something that was very frightening to us, your neurotransmitters or your neurons would start releasing norepinephrine into your bloodstream to get you ready to either get up and run or get up and fight. Okay, so that's what kind of gets your body ready. It's an excitatory, neurotransmitter. Serotonin is probably another one that you've probably heard of. This plays a role in the regulation of our mood, control of our eating, our sleep cycle, how mentally aroused we are, and again, not in a sexual way, but in a I'm awake and I'm paying attention. Also with the regulation of pain and the control of your dreams. Okay, most drugs that are antidepressants try to affect the levels of serotonin in our brain. For example, Prozac is a very well-known antidepressant. It is a selective serotonin reuptake inhibitor, which means it keeps serotonin in the synapse. And we'll talk about what that is in just a second. But it keeps serotonin from being sucked back up so that your brain has some more serotonin to work with. It also, serotonin is released naturally when we are, I don't know if it's when we're awake or when we're asleep. I always get those mixed up. But basically, once the sun goes down, your body stops producing serotonin and you fall asleep. And then when the sun comes up, it starts producing serotonin again and you wake up. Okay, so it helps to deal with that. It can also deal with depression states. For example, in people who live in the far northern reaches of the world, where the sun sets in November and then doesn't come back until February. That's a real thing, by the way. Serotonin is what they're not getting. They're not getting any serotonin and they feel like crap. It's called seasonal affective disorder, or SAD. So seasonal affective disorder is something that you can actually fight with just very bright lights. But we'll talk about that, I think, not the next unit, the unit after. We also have things that mimic opioids, which are called endorphins, which is probably something you've also heard at some point in your life. This is your brain's natural painkillers. The best example that I can give you about endorphins being used in marathon runners, people who are running constantly, their body wants them to stop, and it keeps telling them, "I hurt, stop running." But their willpower to continue to run overpowers that, and your brain eventually goes, "Okay, fine, I give up. If you're just going to keep running, here are some endorphins so I don't hurt as much." Okay, and it's sometimes referred to as breaking through the wall or the runner's high. Okay, that's the endorphins that they're feeling. They're not actually feeling their body anymore because their brain has shut it off with endorphins. Then they're like, you know what? You're fine. Just do whatever it is that you're going to do, but you should stop running. Okay. I have never felt the runner's high because I don't know if you've noticed this about me. I am not a runner. I have a car, and I'm not going to give that up anytime soon to start running. What do I look like? A peasant? Pass. Hard pass. So neurotransmitters are the chemicals that are released by your neurons to communicate with the other neurons. Okay. Now, when the neuron is doing something, it has a couple of different states. The first state that it is in is a rest state. It's not doing anything. It's just sitting there, primed and ready to go for when it gets excited to fire off. Okay. So in rest, it's just kind of sitting there waiting. Then, if the neighboring neurons start sending transmitters to it, the chemicals to it, the neurotransmitters, it can stimulate that neuron into firing. So it can absorb that stimulation. And if you think about it like flushing the toilet, if you kind of start pushing down and you start pushing down and then suddenly it flushes, it's the same thing happening with your neuron. You're getting neurotransmitters, and then eventually it lights off the neurotransmitter, or excuse me, the neuron. Okay, so it gets stimulated, then the cell body depolarizes and shoots electricity, a very, very small amount of electricity, down the axon. Okay, then after it's done that, it has to recover. Okay, now the chemical that it's using to shoot that electricity is sodium. Okay, so salt. So it needs to replenish those salt stores that it's got to be able to get back to a point where it can fire again effectively. Another example of kind of an overfiring is the drug ecstasy. Ecstasy has the ability to kind of hijack this electrical system in our brain and cause your neurons to just fire. And they don't really get time to recover. Okay. Once the drug wears off, your brain goes, I am out of everything. And it just kind of goes into this exhausted state where it really can't do much of anything. And people who use and abuse the drug of ecstasy, if they go to like a rave over a weekend and they sit there and get high all weekend long on ecstasy, they suffer from something called suicide Mondays, which is they are so exhausted and their body just can't do anything, then they fall into kind of a depression because of the fact that their body is just depleted of neurotransmitters and their brain is exhausted and their neurons are exhausted because they've been firing constantly the entire time. Okay, so that's another example of how that kind of a thing can actually happen. Here we have a picture of two neurons zoomed in. We've got the two neurons on the left, and then we have how they communicate with one another there on the right. We have the sending neuron on the top and the receiving neuron on the bottom. And what you'll notice is that they don't touch. Between the two neurons is a gap that we call the synapse. The synapse, or the synaptic cleft, or the synaptic gap, is basically a very, very tiny space. We're talking a few microns across, that basically allow for the two neurons to be almost touching one another, but not. And again, the neurotransmitters, these little chemicals that are stuck in these little bubbles of things in the end bulbs called vesicles, they sit there and wait for them to be to get the signal from the axon to release, and then they release the neurotransmitters into the gap. The neurotransmitters act like a lock fitting into a key. Okay, the lock and the key is the neurotransmitter and the receptor. And only a certain neurotransmitter will fit into the certain receptor on the other side. Okay, and once the receptor is full, the other neuron, the sending neuron, will suck back up the remaining neurotransmitters in the synapse, not wasting any of them if at all possible. So in the reuptake system, it basically is recycling your neurotransmitters and getting it to go back in again. Because, well, if you're not going to use them, I can use them again. And they'll sit there and do that. But like I said, Prozac pauses that reuptake for serotonin so that it allows for the serotonin to just kind of sit in the synapse until all of it gets absorbed by the neighboring neuron. Okay, the receiving neuron will absorb it all, as opposed to only getting a little bit and then having to wait for another shot of serotonin to go in. So reuptake is the system through which we recycle those neurotransmitters. And again, they don't touch, and it's a little bit of chemicals, like a very small amount of chemicals that get pushed across the synapse from one neuron to the next. Okay, they release them, they absorb whatever's not absorbed, gets reuptaked, for lack of a better term. Okay, so that's how transmission works between the two sets of neurons. All right. You can also do this with muscle fibers. So you'd have the end bulb kind of sitting with a synapse to a muscle fiber, and the muscle fiber absorbs the neurotransmitters and then triggers and allows you to move. As the same thing with your glands. It'll send neurotransmitters onto a gland, and the gland will start releasing hormones. We'll talk about that in 2 weeks. All right. We also need to talk a little bit about the nervous system itself. So all of your neurons are part of your nervous system. Your nervous system is made up of 2 parts. You have your central nervous system and your peripheral nervous system. Now, your central nervous system is made up of 2 parts, your brain and your spinal cord. Okay, those are the only parts of your central nervous system, brain and spinal cord. That's it. Okay, the brain absorbs the information from your peripheral nervous system and then sends it out to your muscles to move you out of the way of that train coming. Your peripheral nervous system is made up of 2 parts, the somatic nervous system and the autonomic nervous system. The somatic nervous system controls all of your voluntary body functions. So the fact that you can wave your arm back and forth, that's your somatic nervous system moving your arm. The autonomic nervous system regulates all of your involuntary functions, the stuff that happens whether you're thinking about it or not. For example, breathing, heart rate, digestion. Okay, I don't have to think, okay, digest food, digest food, digest food. I don't have to think that. It just happens naturally. Okay, that natural system is part of your nervous system called the autonomic nervous system, not the automatic. Although the system is automatic, it's called autonomic. Okay, so the autonomic deals with your heart rate. The fact that you don't have to sit there and think beat, 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 which is really, really helpful, because if we had to do that, wow, we would not be where we're at today. We'd be still in a cave somewhere. Anyway, now your autonomic nervous system is split into 2 parts, the sympathetic and the parasympathetic system. Now, the sympathetic system is what gets you keyed up and ready to go in a fight or flight time. So, for example, you're sitting at home right now. Maybe you're in your room. I want you to imagine that you're sitting there and suddenly the door opens and it's a bear. Okay, big, giant grizzly bear. Your autonomic nervous system is going to kick the sympathetic system into gear. It's going to increase your heart rate. It's going to dilate your pupils. It's going to make you start breathing more. It's going to release glucose from your liver so that you can start running or fighting, so that you have the energy to be able to do that. It's going to stop your digestive system. So if you've just eaten something, whatever's in there is not going to get digested anymore. It's going to start the secretion of adrenaline from your adrenal glands, and it's going to stop you from crying. I don't know why, it just does that. So basically what it does is it gets you ready to run away or to fight. Okay, it gives you the energy and it prepares your body for the fight that's coming. Okay, me personally, there would be a me-shaped hole in the wall behind me instead of me trying to fight a grizzly bear. I know I haven't got a prayer against a grizzly bear. Kind of rhymes. But I could maybe, if I'm lucky, outrun it. Okay, so my sympathetic nervous system is going to get me ready to run. Now, this is also why, in some cases, people will suffer from digestion issues when they are suddenly very, very frightened for their lives. You may have been around a person who was so afraid that they threw up, or maybe they peed themselves, or something like that. That is the sympathetic nervous system going, everybody out of the pool, I got to run. Because if you had to go to the bathroom and suddenly there's a bear, you're not going to be able to run very fast if you're kind of waddling because you're about to pee. So your brain is just going to go, you know what? I don't care. Just go. Just go. We got to run. Let's go. And you're going to go. Okay. So that's why people sometimes, do that, especially if they've just eaten, they might throw up, or if they have to go to the bathroom, it's going to release because everybody out of the pool. Okay. So your sympathetic system brings you up and gets you ready to go. Your parasympathetic system is going to bring you back down to normal. Okay. It's going to, make your pupil size normal again. It's going to reduce your heart rate. You're going to reduce your breathing rate. It's going to start the digestive system again, and probably make you hungry because you just burned a lot of energy running away from that gigantic bear. Okay. So you're going to go, your body's going to return to a normal state from that sympathetic panic state. It's going to bring you back down and kind of relax you again. You're like, wow, that was really bad. I was hungry. And you're going to want to replenish the energy that you took out of your system. Okay. So that is the basics of the neuron and the nervous system. So this neuron, again, is the basic fundamental building block of everything that we know about our nervous system. Our nervous system runs throughout our body. We have nerves all over the place. For example, you have touch sensors throughout your body. Your skin has touch sensors. If you were to touch your fingertip, the data is going down your finger, through your wrist, past your elbow, up your shoulder, to the brain to be processed. And then that information then has to leave your brain, down your arm, down your fingertip to go, ow, that hurts. Okay. Which is why if you ever do like a slow-mo of somebody touching a hot stove, you're sitting there watching them hold it there for a long time. You're like, wow, doesn't that hurt? Yeah, but it hasn't gotten to their brain yet because it has to go through this entire nervous system. We don't have neurons running on Bluetooth. We've got to send it up the wire to our brain, okay? So that's the basics. Again, we'll talk more about the nervous system, as well as the brain next week. Not tomorrow, Wednesday. No, it is tomorrow. Today is Tuesday. Wednesday, tomorrow, we're going to quickly go through a couple of things about the nervous system that you might have questions about. And then on Friday for this class, we've got a movie. It's going to be about a group of people who suffer from a neurological disorder that goes undiagnosed for about 40 years. And then they finally figure out that they think they know what the cause of it is. And then they're going to give them some medication to increase the level of dopamine in their body. And they're going to come back, not from the dead, but they're going to come back. Okay. It's called Awakenings. It's a really good movie. Don't spoil it for yourself. Be ready for that on Friday. Okay.